Okay, so you've just turned in that first open channel homework assignment. The next thing on your to-do list is related to the project. I've been fielding some pretty good questions via email, and people have stopped by my office with a few questions about the demand estimation part of it. One of the recent questions I got was about the stadium. My advice about the stadium was just think about when are they likely to use the most water at the stadium. Is it in the evening after the game when they're watering the grass? Or is it during the game when everybody's in their seats? Or is it maybe during halftime when there's a huge line of people using the toilets, which are all flushing simultaneously? People are washing their hands at the concession stands and getting drinks of water and that sort of thing. Just make some assumptions based on the number of people there. How many toilets might they have in a big stadium with that many people, where basically everyone in there is probably going to want to use the bathroom during halftime. So it's not necessarily about using the 1.8 peaking factor and the 3.25 peaking factor in the case of the sports stadium. Those peaking factors are related to just the everyday run-of-the-mill residential demands that you see varying in a population that's spread out over a certain area and people are in their homes. But a sporting event is a completely separate thing where there's a really intensive demand for water all at once. So for each of those special locations where water is going out of the network, whether it's the golf course or the sports stadium, just kind of think through things in a logical and real world kind of way. How is the water actually going to be used at this place? And we got to size the pipes to make sure that they're large enough to meet the peak demands. And just for sake of being conservative, what we assume is that the peak demands are happening everywhere simultaneously. So, the cardboard box factory is operating at the same time as the food plant, which is going at the same time as the football game, which is going at the same time as all of the shops are full of people. So you just want to make sure that the network is sized appropriately, so you have to be conservative when you're doing demand estimation.
Can you assume turf on the football field?
Yeah, it doesn't really matter what's on the football field. It could be concrete because you're not going to be watering it during the game. So I don't think that the irrigation demands are going to be as large as 1,000 toilets flushing simultaneously, or however many toilets it might be. Now turf at the golf course, no. You got to assume grass at the golf course. Any general concept questions related to demand estimation before we continue with Manning's equation?
Are we submitting references with the demand estimation?
Yeah, so if you found some sort of a resource for what's the per capita use for water demand in Seattle, then include the reference. Help me to understand what are your assumptions based on. Yeah. So remember that the submission that you're doing on Monday, March 6th, it's your hand calculations, and in front of that, the summary table, but then also a brief write-up where you're explaining kind of the assumptions that you've made and justification or methodology to help someone who's unfamiliar with the project understand why you're saying that there's going to be certain flow rates at certain locations in the network. So I'll be really grateful if you make the calculations neat and easy to follow, because I will be looking at every page of every student submission. I think it's really important for me to understand, what did you take into account and what's your rationale. So if you can organize your calculations and make it clear to me, for example, how did the golf course, where are the golf course calculations versus the hospital calculations, and it's not just kind of all running together at different parts on the page. If it's kind of linear and progressive and maybe follows the same order as the summary spreadsheet or the summary table that you're filling out, that would be ideal. All right, so I look forward to seeing that on Monday, March 6th. Now today we're going to continue talking about Manning's equation, which I've drawn on I've written it on the whiteboard here. Manning's equation, as I presented it last time, is used to calculate the velocity, meaning length per time, meters per second, or if we're using traditional units and we have this 1.486 factor, then it would be units of feet per second that's coming out of the velocity. Of course, if we want to have flow rate, Q, all we need to do is multiply this by area. And so we could put area in the numerator here above the friction factor, and then that gives us Q. Remember that hydraulic radius is area divided by wetted perimeter. And so because it's area divided by wetted perimeter, what we sometimes do is combine this area, which is outside of the parentheses, with the area that's inside the parentheses for the hydraulic radius, and express Manning's equation as area to the 5/3 power in the numerator, slope to the 1/2, and then the denominator, it's the n value multiplied by the wetted perimeter to the 2/3. So same formula, it's just that sometimes we're going to have some equation for the area. So for example, if this is our bottom width and maybe it's 3 meters, then area is going to be the depth multiplied by the bottom width. So here it would be 3y. If we're solving for y, it's easier for us just to have the variable over here in this a single time rather than 3y in this area and then 3y separately in the hydraulic radius term. So we're just kind of aggregating together in this streamlined version of Manning's equation. And remember, this formula is applicable whether the channel is triangular in shape, if it's trapezoidal, rectangular. Manning's equation can handle all of those. It's just that we have to use different geometric parameters that would describe the area, the wetted perimeter, and so on in terms of the depth, the bottom width, the side slope, and so on. Okay, so this is the example that we didn't get to do in class on Monday. So we're going to pick it up now. We want to find out the flow rate, Q, and we've got smooth asphalt, so we've got a given n value for that. Trapezoidal channel has a bottom width, so lowercase b, 3.5. In this one, the depth is known, so y is 1.2 meters, and the side slope is 2.5 to 1. And this is saying h to v. Any guess on what the h and the v mean in that context? Very good, that's right. Horizontal and vertical. So that's telling us that that in this parlance and the formula in table 10.1, the way that we describe the side slope is with t. Remember that what we assume for a trapezoidal channel is that it's t units of horizontal and 1 unit of vertical. So in other words, t here is 2.5. Okay, so just to summarize, I'll write this on the whiteboard. We've got the following. We've got n is 0.014, b is 3.5 meters, t is 2.5, y is 1.2 meters, and then the slope, s, remember, needs to be expressed as a decimal. So here it's telling us the slope is 0.1%. So that means we have to say slope is 0.001. So that's our slope. So if we substitute it into Manning's equation, it is going to be our area here. We're going to have to calculate using, well, I guess sometimes the way I look at it in a situation like this, if we've got a trapezoidal channel, then I sometimes will break it up into the part of the channel that's rectangular, and so this part of it is simply 1.2 meters by 3.5 meters because it's 1.2 depth and 3.5 across the bottom. And then these two sides collectively, if you add it together, it's like another rectangle that is 3 meters by 1.2 meters. So why 3 meters? Is because if it is 1.2 meters of depth, if y is 1.2, then this side part is going to be 2.5 times 1.2. So in other words, the side triangle here, if it is t equals 2, then what that means is that for 1.2 meters of y, then this top here is going to be 3 meters, because 3 times, oh, I'm sorry, it was t is 2.5, right?
Yep.
Okay, so if we have the depth, 1.2 meters times 2.5, then that gives us this top width here is 3 meters. So the area, in other words, is the rectangular portion, which is 1.2 meters by 3.5 meters, plus those two side triangles added together, which is 1.2 meters by 3 meters. And so the overall area is 7.8 meters. Now, of course, we could use these formulas too. Let's just prove that to ourselves with this. So the other way is using b plus ty times y. So b is 3.5 plus ty, so 2.5 times 1.2 meters times y, 1.2 meters. And I guess I haven't proved it to myself today, so let me get out my calculator here. So 3.5 plus 2.5 times 1.2 times 1.2, 7.8. It works out. 7.8 meters squared. Okay, so that's our area. Wetted perimeter. If we're just looking at the geometry of it, may be kind of the classical way. You know, like if we've got 3 meters across the top and 1.2, then this distance is the square root of 1.2 squared plus 3 squared. And there's one here and one there. So the wetted perimeter would be 3.5 meters across the bottom plus 2 of the side slope distances, which is 2 times the square root of 1.2 squared plus 3 squared. So that ultimately is this part of it being 6.4622 meters, and added with 3.5, then the total wetted perimeter is 9.9622 meters. And I guess we can double check with that by calculating like the W parameter. So just as the check, W here is 1 plus t squared. So 1 plus t in our case is 2.5 squared, and we're taking that to the 1/2 power. Okay? So if you'll follow along just to double check my numbers, 2.5 times 2.5 plus 1, take the square root of that, 2.6925. So W is 2.6925, and then B plus 2YW. Okay, so the wetted perimeter is B, which is 3.5 plus 2 times Y, which is 1.2 meters, times W, which is 2.6925. Okay. .9622. meters. It's the same as we had over here. All right. So you can calculate the area and the wetted perimeter either using this or maybe just using your first principle understanding of the geometry. But the point is once we have the area and the wetted perimeter, we can substitute it into Manning's equation. So let me erase this and make room for that substitution into Manning's equation, because we've calculated the area is 7.8 square meters and the wetted perimeter is 9.9622 meters. Okay, so Q is the area, 7.8 meters squared to the 5/3 power. The slope, 0.001 to the 1/2 power. And the n value, 0.014 times the wetted perimeter, 9.9622 meters to the 2/3 power. Okay, can you put that into your calculator and determine what is the flow rate in this case? 14.9, that's what I got as well. So 14.966 cubic meters per second. Okay, now on the subject of units, this formula is not dimensionally homogeneous. And do you remember what that means, dimensionally homogeneous? It means that the units on the right-hand side of the equation are the same as the units on the left-hand side of the equation. This is not. This is an empirical equation. It's not fundamental. Empirical means it was just kind of based on a lot of observation and calibration and a fitting factor n. Because if we look at the units, we've got meter squared taken to the 5/3 power divided by meters to the 2/3 power, but there's no time parameter there. There's no seconds in slope or in the n value. But yet the Q is going to have units of inverse seconds in the denominator as the time parameter. So it's okay. It's not dimensionally homogeneous, but we do need to make sure that we're putting in, for example, an area up here where it's going to go to the 5/3 power. And if you've got traditional units, then you'd need to have that 1.486 coefficient at the front if you're using units of feet. Okay, so any questions on applying Manning's equation into a trapezoidal channel here? Now this is the easy kind of problem because we were solving for Q, given a depth. The unknown was over on the left-hand side of the equation. It's a little bit more tricky when we're solving for Y, because Y, the depth, the unknown depth, is in two different places. The depth, if we were solving for Y, would be in the area term, and it would also be in the wetted perimeter term. So it's a little bit more tricky when we're solving for Y, and especially because if you look at the formula for area, Y appears multiple times. So it's not an impossibility. We just have to be careful when we're putting into our solver. All right. So I emailed you yesterday a link to this video, and if you're using the Casio calculator, I'd recommend that you review it. It's only 4 minutes long, and it'll step you through the process of how you can use the Casio calculator to solve for an unknown depth. And what makes it a little bit tricky with the Casio is that it doesn't have a full keyboard of all of the letters of the alphabet. One of the things that you have to do on the Casio calculator is you have to map different variables. So like for instance on my calculator I can use Q, B, T, S. It has all those letters, but the Casio only has a few of the letters. And so you have to like say, well, I know that I use Q as flow rate, but Casio doesn't have a Q on the keyboard, so I'm going to assign it the variable A. to represent flow rate. And so then once you construct the equation using the variables that you do have, you can put in an actual number for any one of them, well, all of them except for one, and solve for the unknown variable. So that's what a solver will allow you to do. And we're going to look at a kind of solver today. We're going to use Wolfram Alpha just as an illustration, but you'll need to do it with your calculator for an exam and maybe even for a quiz before the exam. And so, you know, whether you're using a TI, a Casio, an HP, or some other kind of calculator, you need to be able to solve for the unknown depth in your solver. Okay, so again, here is Manning's equation, both in terms of SI and British gravitational units. And finding the unknown depth is oftentimes what we're trying to solve for with Manning's equation. Like, for instance, you'll know a flow rate, and you're trying to figure out how big should the canal be. Like if you're designing an irrigation canal, and someone was to say to you, well, I need a certain flow rate, maybe 5 liters per second. That'd be too low. 5 cubic meters per second going through a canal, and I want it to be 3 meters wide. How deep would the flow be? So that's a pretty standard problem, solving for the depth. And one way for us to do it if we're solving with Excel is to rearrange Manning's equation so that all of the known factors are on one side and all of the unknown factors are on the other side of an equation. And then we iteratively guess for the unknown depth until the left-hand side of the equation equals the right-hand side of the equation. So in addition to using Wolfram Alpha to solve Manning's equation today, we're going to look at an example where we'll use Excel and rearrange Manning's equation in this way, where all of the variables that depend on y are on the left-hand side of the equation, and then the known factors like the flow rate, the roughness, the slope, all of that will be on the other hand side of the equation. Okay, so here's that example where we're going to use a solver and also Excel just to try and find out what is the unknown depth y, the normal depth. Assuming that conditions are steady and uniform, what is going to be the depth of flow in this trapezoidal channel? So it's, you can see 15 meters across the bottom, has side slopes of 1 unit of vertical for 2 units of horizontal, so T equals 2. Flow rate of 175 cubic meters per second, slope of 0.45%, and this must be made out of concrete because the 0.013 is a pretty typical end value for concrete surfaces. Okay, so here you can see I've substituted in for a trapezoidal channel. This is what Manning's equation becomes when we've got a trapezoidal channel. So area, for example, is B plus Ty times y. Wetted perimeter is B plus 2y times W, where W is 1 plus T squared to the 1/2 power. So we're going to put all of this into Wolfram Alpha given the known parameters that we've got. So let's put those on the board to begin with. For example, we know that we've got a trapezoidal channel, and Q is 175 cubic meters per second. The slope S is 0.0045. The bottom width B is 15 meters. T is 2. N is 0.013. Let's see, what else is there? Is that everything? Yeah, all right. And the unknown is, what is the depth? What is y? Okay. So let me start up a browser here, and if you have a calculator and know how to put in this equation, then do that. If not, or if you just want to see how we could set this up in Wolfram Alpha, then you can follow along as I do that. I wish I could just paste this equation into Wolfram alpha, but I don't think it's necessarily that easy. So let me do my best here. So Q 175 is equal to B, so that is 15 plus T, T is 2, times Y, so that's our unknown depth, and then times Y again, and I need to put in another set of parentheses here, take it to the power of 5/3, times the slope, which I know is 0.0045 to the power of 0.5. And then I want to divide by, divided by n, so 0.013 times, now we're going to put in the formula for the wetted perimeter, so that is B, so it's 15 plus 2 times Y, the unknown, 1 plus T squared, so T is 2, so 1 plus 2 squared, and this term is taken to the power of 0.5. And then one last parentheses, everything to the power of 2/3. I'm just double checking here to see if it looks right. Now, of course, the divided by thing doesn't go all the way over, but that's okay. It's still going to have the same mathematical effect if I divide only the slope by this as the entire expression by that, since it's multiplied here. I think I'll be okay. So now when I click compute, it's going to go through the step of graphing and kind of restating the formula in maybe a little bit of a sharper way. And we'll solve down here for y, 1.572. And anybody else get the same thing for the depth? That is the right depth, by the way. That is the right depth. So if it's really easy, you know, to get one exponent wrong or to type something in incorrectly, but let me bring it up on the screen here. So if you calculate the W term, then the depth that we're looking for is 1.573. So, you know, like here with Wolfram alpha, I've showed you how to solve this with like a numerical solver. Y is in several spots in the equation. We couldn't just rearrange it algebraically and solve for Y that way. You could iterate, you know, just take a guess of Y and keep changing things around. And that's effectively what we're going to be doing with this. So here's the same example now in a spreadsheet. So in this example, you can see I've got the formulas for everything. So let's put in what we know, 175 cubic meters per second, and the B value is 15. The roughness 0.013. The slope 0.0045. Side slope is 2. Okay, so now W I'm calculating with this formula here. Let me make it a bit bigger. So it is 1 plus T squared to the power of 0.5. So we got W. And now for Y, I'm just going to have to guess some number. So let's say maybe it's 1 meter. I'm going to use goal-seek to change this guess. I'm going to continually adjust that guess until this target cell, which is where I'm going to be finding the difference between the left-hand side and the right-hand side, is 0. So I'm just starting off with the guess 1 meter. Okay, so if the depth is 1 meter, then what would be the area in that case? So here I'm now going to use the area formula. Oops. Okay, so the area formula is the b plus ty times y. So it is b plus t times the guess of y times the guess of y. So if the depth is 1, then the area would be 17 square meters. Wetted perimeter, here's our formula for wetted perimeter. B plus 2y times w. Okay, so B plus 2 times y times w. Okay, so again, this is just kind of a contingency calculation, all depending on if the depth was 1. So then the hydraulic radius is the area divided by the wetted perimeter. Okay, now by LHS, that means left-hand side of this equation. So the left-hand side of this equation is the area times the hydraulic radius to the power of 0.6667. That's the 2/3. Okay, so that's the left-hand side of the equation. The right-hand side of the equation is n times q divided by the slope to the power of 0.5. Okay, so now I've got the right-hand side of the equation, and the right-hand side of the equation is constant. It's not changing because y does not appear on the right-hand side of the equation. So when I change my guess for y, it's going to update the left-hand side. And what I want is I want the difference between those two to be 0. Because when the difference is 0, then that means I have the depth that's going to make this expression equal. So for example, if I switch from 1 meter to 1.2, it gets closer. The difference is getting smaller as I increase y. And what we want to do is have the solver with goal seek say we want this cell to be 0 by changing the depth. Okay, and as soon as we let it do that iteration, it minimizes the difference and it finds the depth should be 1.572, and that's the depth in meters, the same depth that we could calculate using the solver. All right. So this is something that's going to recur again and again from now until the end of the semester, needing to solve for the normal depth in the trapezoidal channel. So I hope that you'll get really good at it because you're certainly going to get a lot of practice. And so, you know, whether it's using Excel or using the solver or, I mean, actually both, you need to be able to do it both ways. You should be able to solve for the depth in a trapezoidal channel when you're given a flow rate, bottom width, side slope, channel slope, roughness, and so on. Okay, so any questions about that? All right. Now, I mentioned that table 10.1 has the geometric parameters for a lot of different shapes. So you can see it's got the geometric parameters for a rectangular section, which, I mean, probably you wouldn't need its guidance for that. You know, the area is just the bottom width times the depth. The wetted perimeter is the bottom width and 2 times the depth because you've got these side portions where the water is in contact with the edge. The geometry is a little bit more tricky, particularly for like a circular channel where it's not flowing full. Do you notice this circular conduit where the depth is y, meaning it's not all the way full? The hydraulic radius isn't just the diameter divided by 4 if the pipe isn't full. Hydraulic radius is only d divided by 4 if the water's all the way to the very top and the entire circular wetted perimeter has resistance that's being applied to the liquid. But when we are designing things like storm sewers and sanitary sewers, then we have to take into account the angle that the water is making with the center. So you can see here theta, and we'll get to that towards the end of the semester when we're doing some design related to sewers. But I just wanted to point out now that Table 10.1 has that geometry for a variety of shapes that you'd need. And typically the tricky, the hard kind of question that you're likely to see on an exam or in the real world, honestly, is finding the depth. Finding how deep the water's going to be in a channel with a certain shape. Okay, so now let's get a little more practice. I'm going to give you this one. I'm going to stop talking, just pause for a moment, give you a chance to try things out. Whether you want to use Excel, you can get out Excel if you want to. I'll bring up that spreadsheet template just to show you and remind you what it looked like. So you can use your computer. If you want to go to Wolfram Alpha, that's okay, or you can do it on your calculator. But one of those three methods, I'd like you here to find out if we have 29 cubic meters per second going through this channel that has a 3.5 meter bottom width, then what will be the flow depth? What is y? Solve for the normal depth. Okay. So if you use the solver, well, either way you do it, I think you should get that the depth is 1.66 meters approximately. Here you can see the substitutions that I made into the equation. It's sometimes a little bit easier to see everything written out by hand than it is on the spreadsheet. So let me do it by the spreadsheet now as well. Okay. So for our flow rate being 29, the bottom width is, I guess in this new example that we're looking at, it is 3.5. Okay, 1.657. So that kind of confirms what I got through the solver as well. All right, so we did 3 problems today with trapezoidal channel geometry and Manning's equation. You'll have some more practice on the next homework assignment, which I will get loaded into Blackboard, but I think the more immediate thing on your agenda is the demand estimation. So if you have any questions, feel free to let me know. I'm available for a few minutes right now after class, but I'm actually headed back over to the hospital. My son's in surgery right now, so I won't be here for the rest of my office hours this afternoon. So just send me an email, or you can call me on Teams. I'll be accessible that way. So see you Friday.
Is that homework due Wednesday?
I don't know. Let's check.